In this video, we're still going to be solving areas of regions within graphs. So if you are new or this video has located you, we actually have a series where we have been calculating these types of questions. So you can go and check them under my playlist and see how we have been able to solve these ones successfully. So you are given a function that you have your cos of x over 2, then they've given you your x that is equals to your pi and your 2 pi. So I know most of the people, they start panicking when they see the trick and when they also see your radians. So one quick tip, when you are dealing with your radians, you can actually convert them and work with your degrees so that you can be faster with your calculations. So we have the formula that says your degrees equals to your radians, then this is multiplied by what? This is multiplied by your 180 over pi. So but if you already know your radians well, you will know that your pi is equals to 1/8. But everything that we do, you know that we have to prove it mathematical. So if we want to work out these degrees, we'll say we have our pi is a radian, then we multiply this by 180 over pi, then this will cancel, then it means here we have 180 degrees. So for this one, it's a matter of having to put 2 here. So we're going to be left with 2 terms on it. So I'm also going to do it here, that our degrees would be equals to, we have the 2 pi multiplied by 180 over pi. This was the radian that I got here. This will cancel this one, then you will have 360 degrees. So now instead of having to work with pi and your 2 pi, you are working with your 180 degrees and your 360 degrees, which will also make this question at least a little bit easy. But if you're comfortable with working with your radians, you can still keep it in that way. But you see, for me, I just prefer working with my degrees. So I know that now, okay, if I'm going to draw my function, how is it going to be like? I will know that, okay, here I will definitely have my 180, then here I'm going to have my 360. You see, because sometimes you can be given something like they say you have your 3 pi over 4 and you don't know what this is in terms of degrees, you see, and you also have to take this one and input it on a Cartesian plane. So the safest way it will be to always convert to your degrees, then put it here, then after you are done with this one and you want your Cartesian plane or your graph to look fancy, it is then that you can take this one and put them here. So I was just showing you one example that they would use. So now you have your 180, and remember, since I've converted this one, it means when I'm getting to this point, these ones are already my x values that I've worked out. It means I just have to input this one into this one. So I will say I have cos of, what will I say? I will say I have cos of 180 divided by 2. You see, this is the same as having your cos of 180 divided by 2. This is going to give you your 90, and cos of 90 gives you what? Cos of 90 gives you 0. Then it means you now have to come and indicate that the 0 within the graph, that it's going to be there. Then now you go and say for the second one, you have cos of 360 divided by 2. Then this is the same as having what? This is the same as having your cos of 180. Cos of 180 gives you minus 1. Then minus 1, you can say it's going to be somewhere there. Then I just wanna do it like this so that I can be able to reference it out. One another tip that I like to use is that each and every time I'm given these x values, I also like to do it like this, so I know I'm not supposed to actually take anything sorry about that. I'm not supposed to take anything that is outside these lines that I'm drawing. So basically here you have that pi and that 2 pi. So as I said, the second point that I'm having is this one, which is my minus 1. It means now I'm going to be having what? I'm going to be having a shape that looks like this, and this is the exact region they are looking for. So you will have to work out the area for this region, you see. So how did I know that this shape is going to be like this? I know this shape is going to be like this because I know the original shape of cos of x graph. So our cos of x graph, it has a shape that looks like a W. So it goes something like this, you see. But in this instance, ours, it was this portion from here to some portion which is going to be there. And another second factor that you have to remember is that this graph always oscillates. It oscillates between 1 and this side, it oscillates between, this side is going to be between -1 and 1. So oscillates just means that it goes up and down between 1 and 1. That's basically the range, you see. So knowing this graph, then I know, okay, this is definitely going to be the shape. Hence that's why I drew a shape like this, because if it was going to come up, it was going to be something that looks like this, you see. But now we are not interested in this part, we are only interested in the part that you see that is in red. So now we still have to continue with the calculation. So I'm just gonna erase this one out so that I do not confuse you guys. They are only interested in this one, and also this, our x being equals to pi and x being equals to 2 pi. It means we are strictly given a restriction that we are supposed to be working in between pi and 2 pi. We're not supposed to take anything outside that. So we said we can simplify this one for ourselves. We said it's going to be 182 to 360. You see, so since we've done those part, the second part that now comes, it's for you to be able to determine the antiderivative for this one. See, so you have to determine the antiderivative for this one. Then you'll find the difference between your B and your A. So what do I mean by the difference between your B and A? So we know, let me just erase this part. We know mainly that if we're given the fundamental theorem, what do we have? If we have f of B and A, then we have f of x dx. This is the same as equals to your f of x. Then this would be in between the region B and A. So this is the same as having the difference between your B minus your A. So in this instance, our A, it's always the smallest number. Our A will be the smallest number or small number. Then our B will be the big number. So because we have been on a series doing these things, I assume that by now at least you are familiar, and if you haven't watched the other videos, you will now know that the next step would be for us to determine the the antiderivative and use the fundamental theorem to calculate this exact area. So this is basically the formula for your fundamental theorem. So this is your fundamental theorem formula. Fundamental theorem formula or equation. So okay, we have our A and B as indicated here. So in terms of us, which one is going to be A, the smallest number between your 180 and your 360? It now means your A is going to be the smallest. It means here we're going to be having that 180, then this side we're going to be having that 360. You see, so that's why you would then see that they would write it in this instance, that you will see here they would write 2 pi. Here you have your pi, then you have your cos of x over 2. Then this you have to determine it between your 2 pi and your pi. So this is how you would see it written. So now we said we have to find the antiderivative of that one. What would be the antiderivative of your cos of x over 2? So with this one, the antiderivative of such functions, I normally like to use your U substitution method. So, but if you can use any other method that you are comfortable with, then you're more than welcome to do that. For me, I use the U substitution method. So with the U substitution method, I know, let me just write it here. I said we have this, here we have that 2 pi, here we have pi, we have cos of x over 2. So what are we going to say? So I'm just do this. With the U substitution, we basically choose the part that is more complicated within this function. So the one that is going to be complicated or make us work hard is going to be which one? It's going to be x over 2. But imagine if now we were able to just like exchange this x over 2 by u. It will actually make this whole thing easy to work with, because we have an indefinite integral a rule that says that each and every time we have an indefinite integral of what? Of cos of x, it means now we're going to be having sine of x plus c. So that's one of the formula that you have to remember. So when we're using the U substitution in conclusion, we always look for that part that if we replace it with U, it will actually make that part that we are focused on much easier to handle or to calculate. You see, so if we put here, you can confirm that it's going to be easy to work that one out. So what am I gonna say? I'm gonna say I'm gonna say let x over 2 be equals to u. So I'm just gonna be slow as possible then. But what is the differentiation of u? So I will say I have my differentiation of u. I have x over 2. This is the same as having 1 over 2. But remember, here they would have written it in this form. You have your cos of x, then here you have your dx. Then here we're still we're differentiating in terms of dx, meaning I'm going to be writing my dx. Why am I doing this? I'm doing this because I want us to be able to substitute whatever that we are having here to a region where we see our dx, because we're supposed to make our dx the subject of the formula, meaning where we see our dx, we are going to be substituting with whatever that we have here in terms of u. because we are no longer going to be working with x values, but we are going to be replacing those ones with u. So what are we going to have? We're going to basically divide this, then we will have our du divided by 1 over 2, then this will be equals to, you have your 1 over 2 divided by 1 over 2, we have dx. Dividing by this is the same as multiplying, because when we multiply we just turn this, we will have du multiplied by 2 over 1. This would be equals to 1 over 2. We still do the same, multiply by 2 over 1, multiply by dx. These ones will just cancel each other. Then this side you have your t du, your 2 du is equals to your dx. It now means if you are seeing your dx at the top, you're supposed to replace it with your du. So we can see the dx this side, and remember here we're going to be putting the u, then this side the dx is going to be represented by the du. So I'll just explain it one more time so that you guys are not confused. Remember, we were given cos of x over 2. So I said, okay, how can we find the antiderivative of this one? I said, in order for us to find an antiderivative for this one, we can find it using the u substitution. Then if we are working with the u substitution, what happens in u substitution? When you are working in u substitution, you always look at that one part that if you replace it with the u, it's actually going to make your calculation way much easier. And we agree that, okay, if on this one we replace the x over 2 by u, it's actually going to be much easier. Then okay, that's that. Then we say let x over 2 be u. Okay, but now we have to differentiate u in terms of dx, because we were given dx. What do we get for that? I said we're going to get 1 over 2 dx. How did I get this 1 over 2? I got this 1 over 2 because this can be written as 1 over 2 multiplied by your x over 1. Then if this is the same as having 1 over, this is the same as having your x over 2. So if we differentiate this part, we're going to be left with 1 over 2. Hence, I've written this 1 over 2 that you're seeing here. Basically, this part I was differentiating in terms of dx, so that where I see my dx, I will be able to replace it with what I've got in terms of u. So which is what I did at the end. I got my t2 du is equals to your dx. See? So we still have to continue because we are not done. We are not done. So I think I'm just gonna wrap this one out, unfortunately. Or should I look for a space where we can squeeze? Because I definitely don't want to erase the graph. I definitely don't want to replace the graph. Okay, but since we've written them here, or when you are busy, you can just like do your follow-up question and make sure that you understand everything. So how is this going to look like if now we have replaced everything with this? Because now this is the step that we have to write and continue with our calculation. So since I have smaller space here, I can even write it here that we're going to have what? We have this, we have cos of u, then multiply by your 2 du u. So since I have a little space, we'll just use this one. So we are here and we are working in terms of u now. We have successfully replaced everything that has to do in terms of x. So now we can say, okay, I'll just wrap here, sorry for that. Okay, so since now I have cos of u multiplied by 2 du, then it's possible for me to take this 2 to the other side in the meantime and work out whatever is left that side, and when I'm done I will bring it back to the right hand side. So I will say I have my 2, an integral of cos of u, no, yeah, we have our du. You see how clean that now becomes. So what do you notice, or which rule do you know that can allow us to simplify this one? We have one rule that says if we have an integral of cos of sorry about that, cos of x dx, this is the same as what? This is the same as getting your sine of x plus your c. These are your indefinite integral rules. So we definitely have this rule. And just like in your differentiation, you know how your cos is going to turn into your sine. So even in this chapter, we still have something which is similar. So it's just a matter of you being careful with those calculations. So yeah, I meant to say in differentiation, your cos, we know it's going to be minus sine of x, but in this one it's not minus, it's sine x plus c. So it means now where we're seeing cos, we can actually replace it with sine of x, but we won't be putting the c's. So the constant, these ones would be when they just told you to just determine the indefinite integral. So now it means I can say I have 2, then where I have my cos, I can replace it by sine of u du. Then okay, I'm done with this. Then I've also included the correct rule. It means now I'm able to go back and borrow back from what I've written at the first stage. Remember, I said let x be equals to u. So since now I'm at the last stage, it means now I can go back and input the original values that we were given, because we were given x not, oh no, it's not x, let x over 2, sorry for that mistake. I said let x over 2 be equals to u. So since we were given it in that instance, we still need to go and put it into its original state. So now we're going to say we have what? We're going to have to say we have 2, then we have sine of x over 2, then where we see our du, then this is our d of x. So we're just taking everything back. If you've missed the step where I was talking about du and u, you can just reverse the video back and you will actually see why I'm writing my x over 2 and dx here. So what would this look like as your final answer? As I said, the 2 can actually be taken to the other side. You're going to be having your 2 sine of x over 2. So that would be the antiderivative for your cos of x over 2. But now you're going to be working this one between which regions? You're going to be working it between 2 pi and your pi. And we said if you don't want to use your 2 pi and your pi, you can actually use these values, your 360 and your 180. You can even replace this one and say, okay, this side I have my 360 and this side I have my 180. It depends on you and your mood. So from this side, we're going to take this as a function. So we'll say we have this, we're going to use this formula of the fundamental theorem to determine the exact area between this region that we are looking at. You see? So from that 180 to that 360. So what is that going to look like? You're going to say you have what? You have your 2 sine of, where I see my x, I'm going to input what? I'm going to put my 2 pi or 360. But since we were given the 2 pi and the 360, you can input in that way or this way, doesn't matter. Then you're going to have your 2 pi. Remember, this is equals to 2 pi, then this is equals to your pi over x. Then we deduct the other one, which is this one. We will have 2 sine of pi over 2. I like to work it in this way because now I know that when I'm going to be having this is 180 divided by 2 is going to be 90. But when it's pi over 2, sometimes it's confusing. It's confusing, especially if you are not doing it with a calculator. So this is the same as having your 2 sine of 2 pi is 360. 360 divided by 2, then this will give you your 180, and sine of 180 gives you 0. So the first part, this just put it in terms of numbers. So here let's just put 360, then here 180, so you know what I'm referring to. So this is the same as having sine of 180 minus 2 sine of 180 divided by 2, it's sine of 90. So we know we're going to have what? We're going to have 2 sine of 180 at 0. This is the same as having 2 multiplied by 0 minus 2 sine of 90, it's 1. Then this will cancel. 2 multiplied by 0, this is the same as having 0. Then your final answer will give you minus 2. So minus 2 would definitely be the final answer that you are having for this type of problem. And once again, sorry for not having enough space, but as usual, we can only work with whatever that we are having. So it's just a thing that you have to keep up with the way we are doing these calculations. And one another thing that I like to emphasize is that if you also don't remember how to draw your parent functions or your functions like your cos of x over 2, I also made a video that shows you how to draw and to remember the graphs that we have in calculus. I think it's captioned all your calculus graphs in 52 minutes. I'll also add a screen end at the end of this video so that you can be able to tap and be taken to that video and watch it, because in this series we are going to be dealing with a lot of functions, and sometimes it's much easier and quicker if you are able to remember some of the parent function. So what are some of your parent function that I'm referring to, just to give you some quick light? If now you have your x to the exponent 2, this is a normal graph that I know that I've drawn a lot of this graph in my high school or in college. It's actually a quadratic that looks like this, you see. Then I would know my x to the exponent 2, it's a parent function. Now I know if they give me my graph of x to the exponent 8 and they tell me draw the graph of x to the exponent 8 without writing your function values. So they just expect you to just come and write the graph. So I will know that the graph of this would take the graph of this because these are even exponents. You see, it's just that whereas this even number increases, the graph at your x-axis, it widens. Like it's just going to be something much bigger. Let's just say here I have something in terms of 8, I have x to the exponent 48. This is still an even number. It means here the graph is going to be widened, and at the top it's just going to be steeper. So you're going to be having a graph here, it's going to widen and become flat, but going up is going to become much steeper. So this now would mean you know the parent function, and you are able to determine that, okay, if I know the parent function, then what happens now? If they tell me that I have to draw a graph of x to the exponent minus 2, how is that going to look like? I know the parent function, then I can quickly say, okay, my x to the exponent minus 2, that is basically a mirror of this one. It means I'm going to be mirroring this line at an edge of this side. So the first line is from here to here. If I mirror this line is from bottom going up, it means it's increasing. The mirror line, it will always be opposite of whatever that you're having. So it means you're going to be having a line that's coming this side going there. You see how this one is from increasing and decreasing, and this side you're going to be having a line that moves like this. So you're going to be having a line like this and also a line like that. So this red one is your x to the exponent minus 2. Then the black one would be your graph for your x to the exponent 2, not 3. So that's basically how you use your knowledge of graphs in doing these things. You don't have to struggle a lot with remembering the graph, because as I can say, they would also give you your graph to the exponent of 3. So these are odd numbers, and we know the graph of x to the exponent 3, that this, it's a graph that looks like this. It's a cubic. Then now if they ask you to draw a graph of x to the exponent minus 3, you're going to be mirroring these lines. You're going to be having a graph that looks like this, and also a graph that looks like this. You see now, without actually having to calculate everything, I know the graph of x to the exponent 3 and the graph of x to the exponent minus 3, which is going to be for the red lines. It's going to be a graph that goes like this, and also a graph that goes like that. Then now the other ones that they would ask you is to determine your domain and your range. So to go, make sure you go and watch the full video on those functions, and at least come back understanding these functions much better, so that when we carry forward, you are able to know, okay, this I can do, this I don't know the function. And remember, if you are having a cost graph and or any other graph, because your cost graph, we've talked about it, that it's a graph that is going to give you a W shape. Then with the sine graph, you know that, okay, it's a graph that actually shows your two two S shapes in either both of the side. It always starts at the center and it goes up, then it goes down. Even the side is going to go down, then it comes back to that point. It always starts in this point no matter what, but the negative one will also start at this point but go down, then go up. So it's going to be something like this. So you would know the red one is definitely a negative 1, then the one in black would definitely be a positive 1. So those are some of the basic information that you're supposed to know on the functions. So I don't want to add another lecture on top of a lecture, so I would prefer that you go and watch that separate video. So yeah, I'll see you in another series or video where now we will be solving the area of a region, but in this instance it won't be in one graph. It's going to be between two graphs, and we will also be given the points. So yeah, bye.